All right. Sorry about the delay there. So today's title slide is not generated by ChatGPT. This is a set of kit foxes who have shown up in my neighborhood in Chapel Hill. There's actually 6 of them. And yeah, I saw all 6 of them last night driving by. Super cute. So the campiness has joined us in spring is here. So we're going to start with a fill in the blank. And I'll let you all work on this prompt. We'll be circulating around. There is a submission on Gradescope. This one isn't a photo submission. It's a fill in the blank submission for which function calls would be valid given the function definitions on the left, fill in the blanks on the right. And again, we'll be circulating around. You'll have about 4 minutes to submit this on Gradescope. One more minute on this. One more minute. Twenty more seconds. 20 more seconds. All right. I'd love for someone in the front right to try and talk me through the variable a is being initialized to the result of some function call, which is the correct function. Great. Here you go.
Okay, so A, it should be a string, and it's the result of a function that takes an int, and the only function that fits that is h.
Great. So we looked at 2 pieces of information here that are important. The observation was ultimately whatever this function call evaluates to must return a string. Absolutely correct. And it takes in an int as a parameter. And so if we scan our function definitions looking at those 2 pieces of information, We see that only h satisfies that. It returns a string, and it takes in an int as a parameter. So we could fill in h for the a function call. Someone in the front left want to talk through b? Yep, here you go.
So it takes an int and returns an int, so that would be f.
F, all right. So we're getting the hang of this. This is going back to some of our early learnings of where our function call is valid. Again, we've got an argument type here of int, and it's being assigned or used in a place where we expect this expression on the right-hand side of our assignment statement to evaluate to an integer, because the left-hand side is being assigned to an integer, so int to int. And f, of course, is the only one of the functions that satisfies that. Let's go back left. Does someone want to take a stab at C? You got it?
Sure.
All right.
So C, since we have 2 inputs, it's going to be E.
Right. So we've got 2 arguments here, and we call this the arity, or the number of arguments or parameters in a function definition is another important piece of information. So it's not only the type, but the arity, or the number of arguments, must correspond to the number of parameters expected. So here we have 2 arguments. We look through our list, and we see that only E has 2 parameters defined. The types do check out. That's also important. So int to int in both places. And ultimately, we're using the result of this function call in a place where we expect the expression to evaluate to an integer, because the right-hand side of the assignment statement has to match the type that we've defined the left-hand side variable to store. And so this would be E. And because I think you all now firmly have the hang of this, and we've, by process of elimination, gotten down to just a place where we have a string as our argument type. So that corresponds to potentially G. And we have an int as our result. That corresponds to the return type of G. And so G would work here. Any questions on this mapping? And yep. H and F are interchangeable, is what you're arguing. So H takes in an int, and F takes in an int, but the return type is important, and so that's the distinguishment. Yep. And so this is a key thing. It's common to think, okay, well, if we can give the same argument type, then that's all we need to care about. But in fact, the return type is important as a part of determining where we can make valid function calls in our expressions or our statements. Other questions on what we're seeing here? As a reminder, this is the submission for Gradescope today, and so you'll select HFEG, and that'll be open for, I think, another 5-10 minutes. So if you didn't do that already, be sure to do that. All right, so the key thing that I wanted to warm up with here is this recognition that the types of arguments, the numbers of arguments, have to correspond to the types and the number of parameters defined in a function. And where you make those function calls, it matters because it's going to evaluate to the return type of that function. Right? So this is things we learned very early in the semester, but they're coming back, and they're important for new reasons today. And I'd like to take some notes on the type of a function. So what we've just established is that the type of a function, or the usage of a function, depends on 1, the number and type, parameters, order as well, order, number and type of parameters, right? So the order of the types is important. So if you have a function that's defined to take a string as its first parameter and an integer as its second parameter, you can't call it with the inverse and expect a correct evaluation. And 2, the return type. Must satisfy the usage in an expression. So anywhere we have an expression, we know that we can make we know that every expression is ultimately going to evaluate down to some type when it's evaluated. And where we use that expression matters. So if we wanted to have an expression, say, where we have some blank, raised to the power of 2, we want this to be either an int or a double, or sorry, an int or a float. And so we could write a function call that's either going to return an int or a float there, and it would be a valid expression. If we wrote an expression that evaluated to a string or returned a string, this wouldn't actually evaluate correctly, or some other type, such as a tuple or things like that. So the return type tells you where you can make use of this function call. And we saw this in our examples, when we're trying to assign to a variable that's type is defined as an integer or whose type is defined as a string, we had to look to the return type of h to see, okay, it does return a string, and that makes it valid for us to use in this place. So we're talking about defining the type of a function. And this is an interesting proposition because we're about to see that we can use functions as values that we pass around in our program, similar to variables. So how do we more formally define the type of a function? Well, this varies language to language, but in Python, we have a type called a callable. Right? So in Python, a function's type is callable, and I'm actually going to write this in green, callable. And then in here, we specify param types and return type. So so let me make this more concrete, where PT is list of parameter types, RT is return type. All right, so we're going to get some practice with this on the very next slide. But the point is, we can say that we can define what a function's type is using this notation and this type. So we're saying callable, which is actually a type we'll see how to use in just a moment. And then, like we've seen, there's a list of strings where we put string in the square brackets, or a set of ints, or a dictionary where the keys are ints and the values are strings. Inside of these square brackets, we're adding some additional information about the type of our function. And by convention, what's interesting about functions is they have a parameter list, right? We've seen we can have parameters with we can have functions with 2 parameters or 3 parameters. So we put the parameter types in another set of square brackets and the return type following that in a comma. So for example, if we had a function definition such as def, I'm just going to make up a silly function, s, where we have a parameter type x, which is an int, and y, which is a str, and let's say this returns a bool. The type would be callable, and then in the inner parentheses, int str, and the return type bool. Let me try and make this fit real quick here. So it's a concise way of capturing all the important information about a function's type, right? The parameter types and the return type. And we're saying it's callable, meaning we can write a function call expression to something that is a function, give it these 2 types as the first part as arguments, and expect that the last type that's defined in this type is going to be its return type, right? So now that we've got this understanding, let's actually practice converting some function definitions to their callable types. And here, we've got the same three functions, and I've gone ahead and given an example for E, but I want to give you all a chance to try. It's a very mechanical and straightforward process, converting or assessing what are the types of F, G, and H. So just write out besides, so similar to how E defines, E would be its type is callable, and because we have two integers as our parameters, we have those types in the first set of square brackets, and then because it returns an integer, we have that following the square brackets there. So I'll give you a chance to work through the rest of these examples, and we'll come back in 3 minutes. One more minute. Hopefully this is pretty straightforward, but if you are confused by this, be preparing questions. We'll have time for that in just a moment. Thirty more seconds, 30 more seconds. All right. So for this first one, for F, again, this is a mechanical transformation. We would say that F's type is callable, and its first type parameter is a list of its parameter types. Well, there's only one, right? So this is the one parameter type. So we would specify int. Oops. And then that list of parameter types is followed by the return type, int. Right? Similarly with G, callable, and then we see that its parameter type is stir, and then it's followed by its return type, which is int. And last but not least, we have callable and int, and its return type is stir. Right? Questions on this process of taking a function definition and extracting its callable type from this. This is about to be important. We'll see why we're doing this and why we care about this in just a second, but it's going to give us some powerful capabilities. Yes?
Why do you always add a bracket into the first parameter type?
Why do-
There's only one value.
Great question. Why do we always add a bracket into the first parameter type even if there's only one value? So behind the scenes, with details a little bit beyond our concern, what we would see is this would be specified as a list of some type, right? And so because that first, we call these type parameters, right? And it kind of makes sense. We're saying some type callable, and here are it has some parameters to distinguish what separates one callable from another. And that first value is just always expected to be a list of other types. Kind of like we can define a list of a function that takes a list of values, and maybe you're passing it a list with only one value, you'd still need to give it a list. Here we just have to give a list of types for the way it's defined behind the scenes. You could imagine a world where you just had this convention, the very last one of these is always going to be the return type and everything else is a parameter type. But this makes it a little bit easier to read. And I believe in the case of functions that don't return anything, the very last parameter is optional, but we'll always specify it as none. But great question. Other questions on this? All right. So now that we've seen what a callable is, I want to give you all a chance to try tracing this diagram that makes use of a new concept. And you can ignore, for the purposes of your diagram, line number 1. Right? So I'm just going to write another note here, even though it's in the title. Ignore this line. We need it in order to write this program, but for diagramming purposes, we don't care. So starting from line 4 and working our way down, try working through this particular example. And I'll get started with you. If you have questions, we're happy to help. You can trust your intuition on the interesting assignment statement on line 9. I'll give you a hint. Or I'll give you what line 9 actually does. It assigns what f is to g, right? We take the value of f, which is a reference to ID 0, and g is now also assigned a reference to ID 0. Two more minutes on this, and then we'll talk through it together. 2 more minutes. One more minute, and then we'll talk through this together. All right. So I've gone ahead and fast forwarded my diagram to line number 11. But just to talk really quickly, I shouldn't skip over lines 8 and 9. This is sort of the important idea here. And I'll mention that we're about to see why this is a big and awesome and incredible idea very soon. In this little example, we don't have a complete picture of why we would ever want to do this. The point is just showing us at the most basic level possible that this is a capability of our language. And so we define a variable g. We say that g's variable type is anything that's a callable that's a function that takes in an integer, a single integer as a parameter and returns a string, right? So any function that satisfies that callable expectation can be assigned to it. And well, we've got f, which is a function that does satisfy those that callable definition. And that's what allows us to, on line 9, successfully and safely assign f, which is a reference to this function definition on lines 4 to 5, to g. The name f in our globals frame is of type callable single parameter int return type string, right? And that's what allows us to assign it to g, which is also declared as the same type. So this is the first time we're seeing a variable name being used as a value, right? So f is being used as an expression. And remember, just like any other expression where we're looking up a variable's value, such as if we had x assigned to an integer and then we later said, y is assigned x, the first thing we would do is evaluate what is f. And we look in memory and we see that f is a reference to the function whose ID is 0, or it's just a heap reference to ID 0, right? And so we take that value, ID 0, and we assign it to g. And it's no different than any other assignment statement in that regard. We're just taking whatever the value is on the right-hand side that evaluates to some stack value, and then we assign that to g, just the same. Any questions on this assignment statement before we carry forward? All right, so we'll see this is, again, this is not the most compelling example for why you want this, but the point is it's possible and it's interesting, and we're going to see very valuable uses of this very shortly, but let's carry this out. So here we see a variable declaration and assignment statement where we are needing to initialize the result variable in our globals frame to the return value of calling g with an argument of 110. So it's worth pausing here and slowly, if we go all the way back to the beginning of the semester, you've now kind of internalized these function call rules so that you can move through them very quickly, but let's think through them step by step. So one of the first things we did was we looked at the name resolution rules. So given this name, do we actually know of something, of a function named g? Well, it looks like that's just a variable, but when we look up what is g, just the same as when we would look up what is f in a function call, we see that it references a function definition, and that's okay. So we can look at this function definition and see that it takes in an integer and returns a string. So in our usage here, it takes in an integer, returns a string, we're totally fine. This checks out, right? This is a valid function call. So now we need to set up a new frame for this function call. So we set up our frame. And here is where things get a little bit interesting. So if we set up our frame and name it g, that's fine in this context. We know what we're talking about. But now that we're dealing with these, with having multiple names referring to one function definition, I actually think it's helpful to, like, in a circle beside of this or a box beside of this, just record that the ID of the function that we're calling here for g is actually 0, so that we know which function definition we're talking about. Because later on, if we reassign g to be some other function that satisfied this callable, we wouldn't know which one we were talking about, but here we know that we're talking specifically about ID 0. It's the function defined on lines 4 through 5. Great. Our return address is 11. Our value for x, the parameter, is 110. And we're ready to jump into this function definition. We jump in, we see an expression. We're first computing 2 times x. That would be 220. And then we're converting that to a string using the string constructor and ultimately returning that. So the return value here would be the string 220. That gets returned back to line 11. So let me clear out my notes here. So the string we evaluated to 20 gets returned to line 11, where this function called a g occurred. And now we're saying assign that to result. So now result is 220. And of course, the output would be 220. Any questions on this phenomenon? Yep.
For like, let's say the number 8, like line 8, instead of the call the line 8 and stir, if it was like int, then would it fail?
Great question. So the question is, if we had redefined callable in this case to be int, and we tried using that in this context, right? We would see in our editor that there's a type error, and we would say, hey, this type checking doesn't match. You're not using this function correctly. In this particular example, it might ultimately kind of run, and you would maybe just get that result is storing an int value, which doesn't really match what we would expect. So Python will often run programs that aren't correctly typed, but that usually means that there's bugs that could hurt you later on. So if you then tried to use that as a string in a way that only a string would work, you would get an error. And when you, for our purposes, when we use, there's some points on every assignment that are put towards type checking, and those points you would see, hey, you used this in a way that wasn't expected. So you should get some heads up in your code editor in VS Code when you're working on this that says, hey, you're using this function call in an incorrect way. And when you do that, it's just very hard to reason about what actually happens when you go and run this program. It might error out. It might make it some way further and then error out. Yeah, good question. Other questions on this? Yep. So in this case, the only function call that we would diagram, the question is, would there be more frames, would be this function called a g. Because we didn't define the stir function or the print function, we don't add values there. But we did store result in our globals frame, just because that's where it was defined outside of a function. Good question. But this would be the only frames we would diagram here. Other questions? All right. One more question, and then we're going to do a little bit of coding together to bring this home. But in this question, I'll let you reason through it, and then we'll talk through it in another 2 minutes. One more minute. All right, I didn't give the back right side of the room a chance to respond. Does someone want to respond with what are the possible valid variables you could use here, or function names you could use here?
Couldn't it be G, H, or E?
G, H, or E? Yes, why?
Because all of them have one int parameter and return an int.
Exactly. So here we see that we can assign to the variable a function, which is defined as a type callable from one int parameter to an int return type. So all three of these functions would be possible here. You know, E, G, or H, right? Int, int, stir, int. So f would not be a valid function to assign to a function, but the other three would be. And this brings up the last point we'll make before we start writing some code together, which we'll come back to why this is all valuable, which is, of course, it makes sense. You can have many different functions that are the same type. And if we can define the type of a variable to be a function, we're going to soon learn that we can write functions, that we can pass in other functions as arguments as long as the types check out. And you might have many different functions that map from an integer to an integer, and many different reasons for doing that kind of mapping. I'll point out one other interesting thing about this. I'm not going to fully implement this, but we could, if we had from random import choice, I believe is the function name. I'm like 90% certain. We could say choice, and oops, there's a function call, and we give it a list of values, and we could do E, G, H. And the choice function, given a list of values, will return one of those at random to you. And this would be a function that, at random, calls one of these three functions each time our program loads. And this is pretty fascinating. We would never have you diagram something like this, of course, because it would be random what you would expect. But the point is, looking at a piece of code, we have no way of knowing which of those functions is actually going to be called at line 22. And that's pretty neat. So we can start to write programs that have more dynamic behavior behind them as we are able to plug in these behaviors. All right, so what we're going to do is I'm going to have you join me in VS Code. And I want to give you all a chance to try writing. We're not going to use anything what we just talked about yet for this. This is all review. Two very simple functions that you'll write in VS Code. So step one, start a new file, lecture directory, named higherorder.py. So I'll have a few minutes for this. So go ahead and define these functions in this file. what we've talked about, we're not seeing quite yet. This is all review for defining these two functions. Should be pretty straightforward. Ooh. I'm going to switch over to my laptop where I've got this going. And I'll give folks, once this comes back in, should be any second now. Okay. I'll give you all a second to be sure that yours looks something similar to mine. I can test this out, 4.0. All right, 2 more minutes to catch up here. And if you're already there, where we're about to go is define a double function. Similarly, define a map double function. Similarly. One more minute, and then we'll pick up. Oh, this is wrong. All right. So we've got a very simple function defined and another pretty simple function that is saying, hey, give me a list of numbers, float values in particular, and I will run through each of those numbers, call the square function with each number individually, append that to some resulting list, and give you a new list back, right? So we've defined the square function. It just squares its number, its argument, and map squares will square each element of its list, of the list it was given, and return a new list with those values in the same order, right? Now, for illustration purposes, to bring this demo for this demo to make sense, let's define a double, and this is very straightforward, right? Return x times 2. And we're about to define a map double as well, so let's go ahead and do that. I'm going to put this above map square since we already have map square. Oh, got to name it map double. And so now we have this extra function double and this extra function map double. Right. I'm going to scroll down and try and make this so that we can see at least double and then the 2 functions here. So the question I have for you all is, ignoring the name of these functions, map double and map square, what's the only real difference between these 2 function definitions? What's that? One has, sorry, I missed. Yeah, what's the, sorry, the map double and map square. Yeah, what's the difference between map double and map square? One difference. Yep. The function we're calling. So everything about these 2 functions is the same with one exception. we're calling a function, one function here differently and one function here differently. And so wouldn't it be cool if we could write one function that takes this structure or this algorithm, which we would call a mapping algorithm. This is a map algorithm. And rather than hard coding in or specifying in the definition which exact function we're going to call here for each item, we could pass that in as a parameter. And so let's do that together. Let's write a generic map function. I'm going to do this above the other two. So def map. And here we're going to have some function f that is a callable, in this case from float to float. And we're going to see a type error there for just a moment. We'll have to import callable. I'll come back to that. X's is going to be a list of float, and we'll return a float. Right? And I'm going to just add ellipses here for one moment. And the other thing that we have to do is we have to, from typing, import callable. Right? So this line number 1 is important. So this is what allows us to define callable types. So this is built into the Python language. There's this package called typing, and it allows us to do some interesting things with our data types like we're seeing here. Turn on these lights. So that first line is important for us being able to define the type callable for map. And so now map is this function we're defining that we give it 2 arguments. We give it a function that takes a single float as an argument and returns a float as its return type, and then a list of floats, and we need to finish implementing this. Well, I can once again just copy and paste the map doubles that we had, or the map that we had before, and notice this, what was recognized is the one thing that we had in common, and I'll point this out with a comment. Rather than making this function call a specific function that was defined elsewhere, we're able to define it as a parameter that we give to this function when we call this function. And so we added line 1, and then we added this definition of map. And now, if we wanted to try calling map in our REPL, we can give it a shot. We can say map, and then we have to say which function are we trying to call. Well, maybe we call like square is the function definition that we're using as f, and the list of values is 2.0, 4.0. And we can see that square was called over those values, and the return value is each of those list items squared. Similarly, without writing another loop or writing a new definition, we can pass in a different function. So we could pass in double as a reference here. And notice that rather than squaring each item, we're doubling each item. So the big idea, one of the big ideas for being able to specify the type of a function is that it allows us to write what we call higher order functions like map that say, hey, we've got this algorithm where the general steps of the algorithm are the same, but there's one place where we want you to be able to plug in some special behavior and define that for yourself. So you give us a function that satisfies the types that we say. So it has to be a function that takes in a float and returns a float. And then we can perform the larger algorithm as an abstraction on your behalf without you having to redefine a new mapping function for each time you want to do this. All right. Questions on the example we're seeing here? Yep.
I'm just a little confused. So when you're saying result, you're defining that as a list with floats in it.
Yep.
Why is the return called float?
Oh, shoot. Sorry, that's a good point. I miswrote that. Thank you for correcting that. This should be returning a list of floats. My bad. That is absolutely correct. Thank you for that. And this is true for all of them. This is the problem. Yeah, thank you for correcting me there. So for each of these 3 function definitions, they all return a list of floats. My apologies for getting that wrong in the initial drafting. So those wouldn't have passed type check. Other questions on this map definition? Yep.
Why does the function work even though my return type is float and not list float? It's still able to return the list for something.
Yes. So like I said, Python is happy. So we specify types to make it easier for us to check. And so there's a program that we run that I'm not sure why my editor isn't running it behind the scenes, but if I were to try it real quick, I could show you. It's called MyPy. And if I were to try lecture CL15 higher order, we see that there's no issues. But if we check this and we had returned a single float instead of a list, we would see that there is one issue when we run this type checking program. Now, I'm a little surprised that VS Code isn't giving me some red underlining here. I think something must be wrong in my editor. We should have had some red underlining there. But this type checking is something we do in the autograder as well that helps us avoid these logical errors. And it helps us know what to expect, right? So if we look at this function definition, we should trust that we're getting back a list of floats, and that's why we specify them. Good question. All right. So I actually want to show you, so now that we've effectively replaced these two function definitions, if you select the entirety of them, so you'd click and drag and select all of those lines. I don't believe we've talked about this before, but it's a very valuable feature in your code editor. That's true for Mini, where on Mac, if you hold down the Command key and press the slash, or on Windows, you hold down the Control key and press a slash, what this will do, and you can toggle it, is it either what we call comments out or uncomments blocks of code all at the same time. And so we can comment that code out and make a note that the below definitions were abstracted out to the above higher order function. Right? So we no longer need to define these sort of redundant and super specific functions like map, like map float, or sorry, map double and map square. We can now write one function that we pass in as a parameter, the function that we want to use for each individual item. Right? And so what's fascinating here is we have this f being called for each item, but we can specify f when we want. So we can add another function here, like def add 1, x is a float, returns a float, and return x plus 1.0, right? So all we've done is defined one more new function, and after doing so, we could say map add 1, and then 1.0, 2.0, 3.0, and see that now we're able to call this map function, which is a higher order function, with add 1 instead of double or square, but we get to still use it with the others. So this gives us the ability to write a function which we're able to plug in a little bit of behavior, some logic to, for one key piece of its algorithm, which is in this case, how do we map from one input value to one resulting value in our result list? Questions on this? All right. It turns out this map function is actually built into Python. It's a classical function that's been around for the ages, and we'll show you a little bit more about that in just a second. I think it's worth, because we made all these calls in the REPL. Let's go ahead and add in our notes example calls using map. So for example, we can define a list of values or inputs, list of float, 1.0, 4.0, and these are whatever you want them to be, 5.0. And then we could say print map, and then double inputs, print map square inputs, and print map add 1 inputs. Right? And so just to add some example calls so you can see how that comes together. And notice that we're giving as that first argument value a name or a reference to the function we defined early in our program, right? Any questions on this? Map is the first of a few higher order functions that are very classic and highly useful and common in modern day software engineering. The general algorithm is given some list of values, transform that based on some function that changes only one value. We can use map to apply that function to every value in the list without having to write a loop, without having to redefine that logic. All right. So we have one more little piece of, we've talked about for-in loops with sets and dictionaries. With sets, a for-in loop will iterate through each item in the set, and a dictionary iterates through each key. I want to show you, we haven't done this with lists yet, but it works with lists as well. And this will give us a way of simplifying this map implementation. So I'm actually going to copy this, and we'll add one more implementation above it. I'm going to comment this one out. And the classic pattern for if you find yourself writing a loop that starts from 0, iterates over every index in a list, and does something with each value in that list, which this set of code does meet that criteria, we can simplify our code. So with a for-in loop, we can actually write, I'm going to delete these 2 lines. For x in x's, we call this, and we don't have to keep track of a variable. All right? So this definition of map is using the for-in loop, which we've learned about with sets and dictionaries. But when it's used with a list, it's very similar. It will go in order, so it'll start from the first value in our x's list, and continue moving through each item. And the variable x, we don't have to do it ourselves. It's done by Python for us behind the scenes. X is assigned the next value for each index in x's one by one. And so these 2 implementations are exactly equivalent to one another, but this is using the for-in notation. And we're going to get some practice diagramming with this. Basically, if you diagram a for-in with a list in this way, you'll have an x variable that just gets replaced with each new value for each iteration of that loop. This winds up being, now that we're comfortable with while loops, again, if you find yourself wanting to loop through every item in a list, this is the more idiomatic way of doing it. Simpler because we don't have to keep track of an index. We don't have the possibility of creating an infinite loop by forgetting to increment that index, and so on. So we're going to switch over to a diagram. And this one is worth following along with, that really emphasizes this concept of a higher order function and trying to diagram it. So it's taking that map function we just defined. We've got a have function, which implements the callable type from float to float, where you have one parameter type float. And then gives us some practice diagramming a higher order function to see how this actually comes together in practice. Again, you can ignore line 1 for the purposes of diagramming. We don't diagram import statements from the standard libraries. Because we're seeing a new idea here, we'll pick up and work through this together in 2 more minutes. Probably not quite enough time for you all to get through it. Don't stress about that, but make it as far as you can. One more minute. And I'm going to go ahead and start getting the easy stuff set up. All right. So we reached the point of this function call, and this is where we start to see the value of being able to define these callable types as parameters. And we start to have to reason through it, right? So let's zoom in here and make sure this is a valid function call. So again, we ask, do we know what map is? Yes, map is ID 0. That's, of course, this function defined here. And then we check, do the types of our arguments correspond to the types of its parameters? So have, we look up, have is the ID 1, right? So that's type callable from float to float, right? So that's type callable from float to float. That does check out. Have does satisfy this callable type definition, so great. And then values is defined as a list of float, and if we looked it up in our, it's ID 2, we could see that. It's a list of float, and that corresponds to this parameter definition. So this is a valid function call to the map function. Well, there's one other piece we should just triple check, which is our return type. List float, that corresponds to where we're using this expression. We're trying to assign it to a list float value. Great. So Everything checks out. So let's set up this call to the map function. Right? So we set up a frame for map, and our return address is line 16. And we have two parameters. We have an f parameter. F is being assigned what have is. So have is ID1, and f is going to be ID1. Right? ID1 is the function defined in 1112. Right? And then we have values. We have x's is the parameter name. And that's being assigned what values is in global, so that's ID2. Right? So these references check out. And now we jump in, and we see that we're setting up a results list that's currently going to be ID3. It's an empty list. I'm just going to write FL for short and time. It's an empty list. And then we have this for-in loop. So how do we work with a for-in loop? Well, one of the reasons why we tend not to diagram these is because they're a little bit, you have to keep track of a little bit more in your head. It's a little less mechanical or on paper and obvious than using a while loop with an index. But let's do it nonetheless. So we start with, a for-in loop is always going to start with the first value. So if I just draw a red notice here, the first value in this list is going to be 2.0. So the first value of x, when the first iteration of this list runs, or this for-in loop runs, we would have a value of 2.0, right? And then we reach line 7, where we have to evaluate a function called f with x. All right. So what is f of x? Well, I've got to give myself a little bit more space here. We're trying to evaluate this term, so f x. So we look up what is x. X is 2.0. And then we look up what is f. Well, f is the function whose ID is 1.0. So I might just write in ID 1 for illustration purposes. And so we look and we see that's the function defined on lines 11, 12. That's our have function. That's what we're trying to call here, right? So we set up a new frame. And this would be for, it's the function call is to f, but this is why we start keeping track of, ID1 is the function we're defined, that this was bound to. And now we have a return address of line 7. And we have an x value that is 2.0. So x is our argument that is 2.0 that's being passed through, right? And we know that because this is ID1, we're actually jumped into this have, and we're at line 12 that we're about to evaluate. Before I go and evaluate line 12, x divided by 2, questions on this step that we just made? Yep. How do we figure out x is 2.0? So this has to do with this for-in loop, right? So this for-in loop is equivalent to a loop where we have I int 0 while I less than length x is, and then the first line would be x is a float, that is x is I, and then I plus equal 1 down here, right? And then the same things here. So the point is, this x that we would have defined before is automatically, when we use a for-in, the meaning of this x is as if inside the loop we've defined a variable named x, and it just gets assigned the next value of our list, right? Each iteration. And so the first value of this list, our list is 2 and then 4. Why am I not? There we go. The first value of this list that we're iterating through is 2.0. And that's how we got x to be 2.0 as the first value inside of this loop, right? Does that help? So it's the first value, and when you're in one of these for-in loops, you'll have a variable name that is the x here. That's just a variable we've defined. We could have named it anything. We could have named it foo, and it would have been a variable named foo, and it'll just be the first value and then the second value. All right, so just to bring this home, our return value here is x divided by 2.0, that's just 1.0. that gets returned to line 7. And so on line 7, we're taking that return value 1.0 and appending it to our result list. Right? So now our result is ID 3. It's this list here. We append at index 0, 1.0. Right? And then on the next iteration of this for in loop, we're moving to the next value in our x's list. The next value in our x's list is no longer 2.0. It's now going to be 4.0. Right? So we move to the next value. And what we just learned is that's what's being assigned to this x value. Oops. It was originally 2.0. Now it's 4.0. Right? And then we go back into this loop, and we have to call f of x again. Now x is 4.0. And we go through the same set of steps, right? So I add one more frame. We're calling the function f. The ID is 1. That's our have function. X this time around is 4.0. Return address is still line 7. We know that this function is just dividing by 2 and returning that value, so x's value is 4. 4 divided by 2 is 2. So the return value here is 2.0. We return that back up to line 7 where we called this, and that's how we append 2.0 to our result list, right? And so now our result list has at index 1 a value of 2.0. And then ultimately, we reach this return statement, right? So we're done with x's. We've run out of items to iterate on. Our list is completed, or sorry, our loop has completed its work through our list. And now when we return result, we look up, okay, what is result? Result is ID 3. So our return value is ID 3. We return that to line 16. That's where this whole map algorithm was kicked off. So ID 3 is what this function call evaluated to. And so now Wise is being assigned ID 3. And when we go and print Wise, the output would be the list 1.0, 2.0, literal. Right? And so what we're seeing here is an example of a higher order function. And it's no different from what we've been doing before. We just have to be a little bit more careful to keep track of which function are we actually calling, because we aren't sure of that looking at it for the first time around. That's all I got for today. The next exercise is the current exercise is due tonight. And we'll see you back here after the well-being week. And